Okay, welcome to class. We'll go ahead and get started. We finished chapters. God, we covered a bunch between the last midterm and this midterm. We did chapters 4, 5, 7, 8, 6, and 17. So that's 6 chapters, is that right? 6 chapters. Obviously, I can't test you on all of that material, right? So like always, the study guide will greatly reduce the total amount of stuff that you need to study for, okay? So I wrote the review, the study guide for the test review. It's up. I probably should go back and look at it one more time before the review tonight, make sure that it's all there, but it should be very close. The review will be tonight in this room if it's available. If this room's full, it'll be one of the adjacent rooms from 5 to 7. If you can't make it, as always, I'll record it and put it online. This midterm, I guess technically you can bring the note sheets you had on your previous midterm and one additional one. Doesn't matter to me if you bring 3 sheets, that's all right. Any other questions about the midterm? Okay, it's on Friday. It's the next class. Yeah. Your note sheet? No, I don't care if it's handwritten or not. If you want to scan something and shrink it. If you can fit on one sheet. What's that? I guess you have now 3 sheets. All right. If you can get all 300 pages onto 3 sheets, go for it. Okay, so I guess we're going to go ahead and dive into a new chapter then. This next chapter is kinetics. This semester we learned about, the second chapter we got to was thermodynamics. And thermodynamics was this interesting concept because it told us whether or not anything should or should not happen in the whole universe, right? Does this phase turn into that phase? Does this crystallize? Does this break? Free energy can tell us all those things. But what it doesn't tell us is how fast those things happen. And sometimes things can happen on such a slow scale that they essentially never happen. And we've brought this up before, but the diamond on your wedding ring is, from a thermodynamic standpoint, that should be turning into graphite every single day. But in practice, it's never going to happen, right? Because there's a kinetic limitation. So what on earth do kinetics mean? We're going to dive into this chapter. So our learning objectives are as follows. First, we're going to identify the driving and the limiting forces for homogeneous nucleation. We'll calculate the overall change in free energy as a function of the embryo size, shape, and other parameters. We're going to derive the free energy expression in order to determine the critical radius size for nucleation. How big does it have to be before it nucleates? We'll calculate the overall rate of transformation. We might not get to this today. But to do that, we're going to have to take into account nucleation and attachment rates as a function of supercooling. So we'll describe what all this means. And then the last thing, we're going to repeat all those steps, but for heterogeneous nucleation. So what's the difference, and why do we care about both of these? So, all right. This chapter, well, I'm calling it kinetics. I think the chapter calls it phase transformations, right? A phase transformation is something where kinetics are important. How quickly does it transform from one phase to another? Graphite, diamond turning into graphite, that's a phase transformation. It's changing its phase, okay? So we'll talk about the basics of that. We'll do that by starting with going from a liquid to a solid. You have something that's molten, and then when you cool it down, eventually it's going to crystallize. That's going to be the nucleation process that we'll start out with. But those same principles, even though going from liquid to solid is just one example, the same principles can be applied to all sorts of other transformations, solid to solid. For example, in steel, we've been learning about blacksmiths and all that they do to heat treat and quench and all that. We'll dive into why quenching these different alloys and blacksmith projects results in very different properties, and it has to do with kinetics. Okay? All right, so phase transformations, there's lots of types. There's 3 key types though, right? The first one is diffusion dependent, but the composition doesn't change. So diffusion has to happen. Diffusion, as we learned 2 chapters ago, is the motion of atoms, right? But in this case, it says the composition doesn't change. So graphite to diamond is not a bad example of this because atoms literally have to break bonds and move and make new bonds. Okay? Then there's diffusion dependent, but the composition does change, right? In this case, it doesn't have to just be carbon before and after. The composition can change. So you can introduce nitrogen or oxygen or whatever, right? So it's definitely going to rely on diffusion, but the composition can change. And then the last one is that there's no diffusion, but a metastable phase is produced, okay? The easiest way to think about this is to start from completely one phase and then start to form a second phase. As that first little bit of a second phase forms, how is it going to form, right? There's two options here. It can be homogeneous or heterogeneous. What's the difference? So for homogeneous, let's assume two containers, both holding a liquid. So inside of these containers, it's 100% liquid, whatever. Water, molten metal, whatever you want, right? It's all liquid. But if you start to cool that thing down in both of these containers, you've got two options. A solid is going to start to form, and you've seen this. We have a really cool demo the day after the test, so next Monday we have a cool demo where we'll show you this. But a solid will start to form. The question is, what type of shape will it form? Where will that shape be, and does it interact with the container wall, right? So if you form a nice spherical particle, which is common, right? We'll call that the alpha phase. If it forms right in the middle of your liquid, this is homogeneous nucleation. But another option, called heterogeneous nucleation, is when it forms along a container wall. So let's assume it's still spherical. Okay? So you've got your liquid and you've got your solid. Okay? Why should there be a difference? Turns out there's a pretty big difference in energy, and we'll explain why in just a moment, right? But those are the two examples. We have homogeneous nucleation and heterogeneous nucleation. If it forms out of the bulk, it's homogeneous. If it happens on some sort of surface, either the container or an impurity, right? Let's say that you've got an impurity in your material, right? In the liquid, there's a little flake of sand, right? Some sort of impurity. Your secondary phase, the transformation, might form on the surface of that as well, okay? Those would both be heterogeneous nucleation, okay? Now, the driving force for this change in phase, we've already said, is thermodynamics. Thermodynamics, that's Gibbs free energy, says it starts at a higher state and it goes to a lower state. So the change in energy is net negative. It's moving down. Therefore, it wants to happen, okay? But if we ask this question, right, so the change in free energy is negative, which tells you it should be spontaneous. And I'm just going to label these things beta and alpha, but this could just as easily be liquid and solid. Same thing. It's just one phase going to another. If it's a net negative change, then it should happen. To modify this expression, we're going to take our free energy and we're going to divide it by the volume on a per molar basis, right? So 1 mole of substance occupies some volume. If we take our free energy and we divide it by that volume, you get delta G sub V. All this is, it's the change in free energy on a volumetric basis, right? Which is helpful because sometimes when things form, it's more useful to think about the volume of object that forms. For example, the volume of this sphere. It's easier to think of that than to think of the number of atoms involved in it. Okay, but that's all that is. Delta G sub V is just the Gibbs free energy change going from one phase to another on a per volume basis, okay? So the question I have for you is, if the change in free energy from one phase to another is negative, and it ought to happen, why should there be any resistance, right? Should there be anything stopping this? Shouldn't it just be automatic? So what's going on here? What's happening here is that there's surface energy that we have to account for. Think about it. In both of these scenarios, when you form a solid alpha particle in that liquid phase, you created an interface. What do we know about interfaces? Yeah, this has a surface area. And that surface area is associated with a surface energy. How come? Yeah. Yeah, you have bonds that are unsatisfied. The material would like to have some ideal number of bonds, which it has the bulk of the material. It doesn't have those on the surface, so it's costing the system energy. It may not be very much, but it's costing it energy, okay? So think about it. You've got competing forces. On one hand, on a per volume basis, the volume of that sphere says there's a net benefit to turning from liquid to alpha. But you have to balance that with the penalty that you pay by forming a surface area. Okay? Everybody with me so far? Yeah.
For the per unit volume of the Gibbs free energy, when you change phases, isn't there also often a change in volume? So which volume do you
Yeah. That's a good question. Let me come back to you on that. I don't know the answer to that right away. I assume, I don't know. I will come back to you on that.
Okay.
I think what you'd probably do is take G beta and G alpha and make those divided by their respective volumes, and that's how you'd account for both of those. But let me confirm that next class. It's a good question. Okay, so our overall change in free energy, we can't just account for the volumetric term. We have to account for surface area. So let's assume a really simple model where we have a spherical nuclei, okay? If our samples that form, the solid that forms is a little spherical nuclei, then this would be our expression. The total change in free energy, delta G, going from liquid to solid, would be the volume of a sphere, that's 4/3 pi r cubed, right? That's the volume of a sphere. And that's going to be multiplied by the change in Gibbs free energy on a volumetric basis, right? Delta GV. And then you're going to add to that term this 4 pi r squared. That's the surface area of a sphere of radius r, okay? So that's the surface area for a sphere, radius r, multiplied by gamma. Gamma is going to be our surface free energy. Sometimes we just call it the surface energy, right? The penalty you pay for having a surface. Everybody with me so far? That makes sense why we do this? If you were going to do this with a cube or a tetrahedral or an octahedral shape, those things also crystallize. You would modify this expression slightly. Instead of using the volume and the surface area of a cube or of a sphere, you'd use a cube or a tetrahedron or octahedron, whatever you'd like, okay? Which you can look up, okay? Everybody with me so far? So which one wins? You've got two terms. You've got a volume term, and we know that the delta G there is negative. Delta GV is negative. By definition, we've said that this is in a regime where liquid going to solid is favorable, meaning that's a negative term. And then you've got that second term, which is positive. So you have a negative term and a positive term. What happens when you add these two together is the question, right? Do they just stay flat? No, they don't, because they have different dependence on r, right? In one case, you've got r cubed. So as the particle gets larger, the radius of this thing gets larger, one increases negatively by r cubed, right? A stronger exponential there. And one increases positively by r squared. So does this mean that r cubed always wins? Is it always negative? So it depends is the answer. If you plot these things, I think I've got it right here actually. Hopefully. So here I'm plotting negative x cubed plus x squared, right? So I've left out some of the other stuff and I've just put the r dependence here for a minute. The positive and the negative signs are there though. And you can see that as we go from 0 for r, meaning there's no solid formed, there's no atoms that have come together to form a solid, and as you extend this way, that's increasing the size of your little particle, a solid that's forming. Look what the free energy is doing. The total change in free energy actually goes up at first, meaning as that particle forms, you're actually paying a price, right? It doesn't happen spontaneously. And then once you get over the hump here, it's going to start to go down, and then it becomes negative. So this is an activation energy, right? You have to get over a little bit of a penalty before this thing wants to keep on growing. Another way to think of this is that if your atoms were randomly floating around in this soup and they come together and they look like a solid because they bonk together in just the right spot and its change in free energy says that's a good thing, if it's a really small particle, that thing still might dissolve again. It might go down the energy landscape and re-dissolve if it didn't get over that critical size. Everybody with me so far? So let's draw this up. Okay? So common in this chapter is we're going to sketch the energy versus radius curve. So this is the radius of the little glob of solid that's formed, right? Let's assume it's a sphere, so it's a nice spherical glob. That's radius r, and this would be our energy term. The expression is going to look something like this. Okay? Where, again, over some region of r, right here, it's going to dissolve again. So if your particles randomly come together, you have some number of atoms, and this is the size that it's at in terms of r, it will actually shrink back down again spontaneously. It will redissolve. But in this region, all the way out over to here, it will keep growing. Okay? We can quantify the energy barrier. We can say that this barrier right here is an activation energy needed for what we're going to call nucleation. We're nucleating a secondary phase. That little nucleus, this is the nucleation barrier. So that's delta G star. Okay? And the point at which you observe delta G star is R star. Okay? Those are the two important points to take away from this. Yeah, Landon?
So this graph is saying that as the radius of the solids inside the mixture get bigger, then they're likely to dissolve?
Not quite right. It's not the radius of the solids inside it's the radius of the solid nucleus. So it's not like the atoms' radii are changing. Maybe you didn't mean that, but just to clarify, it's not like the atoms' radii are changing. They're staying the same size. It's just that we're putting a bunch of them together, and all of a sudden now that big clump of atoms, we could assign it a radius. If it's a spherical clump, we could say maybe that's a nanometer big, or that's 2 nanometers big, right? And that's the radius r that we're talking about. And there exists a specific value of r, which we're going to call r star, or the critical radii. And if you're less than the critical radii, that glob of solid is going to redissolve again, because it's going to go down the energy landscape this way. But if it's on the other side of your critical radius, it's going to keep on growing. It will never redissolve again. That makes sense? Back to a liquid? Yeah.
So if you had a certain amount of energy to start that wasn't the total energy you needed to get over that hump, would it increase in radius until it hit that curve and then decrease in radius again? Or
So if I'm understanding you, you're basically, instead of starting down here at the bottom, you somehow start at a higher energy level?
yeah, but not high enough to get over the hump.
Oh,
Would it increase in radius until it hit that line? And then
yeah, it still would. So I don't know if you hit this with a laser or something where you're locally heating just that little nucleus. Yeah, you're giving it energy. It still has to get larger than that hump to keep on growing. I think. That's a strange question, but I think that's...
and then dissolve again?
Say again?
So if it was given energy, it would grow first and then dissolve again?
So it will only ever dissolve if you are on the left-hand side of this curve, right? So again, think of what's happening in a liquid. It's a gazillion collisions happening all the time. These things are vibrating, they're moving, there's Brownian motion where atoms are floating all over the place. So there's lots and lots of instances where these things are getting mashed together. And at any given moment, some number of those, it's probably a small number if you're not very far below the freezing temperature, some of them will all of a sudden look like a solid. Like imagine if all the students in these rooms, just like I blindfold you all and you start bumbling about and then everyone say pause, I could look around in the room and I could see, oh, here's a group of square students. Even though they didn't know it, they were sort of blindly bumbling. This is a nucleus. But if this group here, if I assign this a radius, right, going from the center outwards, if it's not bigger than some critical value, then when I unpause it, they're just going to redissolve and go back to being a liquid. But if you get a critical number of these atoms together, then they won't redissolve. It'll keep on growing. Everybody follow me so far, Tyler?
Does this fit with that example we talked about earlier in this class where you have like a water bottle that's in your car? It's like
Yeah, so that's what I'll show you on Monday. So hold that thought. It's really good. Well, it works half the time. We may have to watch a video. I'll do it in class, and it works like half the time. All right, so we've talked about that it's going to shrink versus grow. This is an activation energy. We love activation energies in this class because then we can do things like Arrhenius equations with them. We love working with activation energies, okay? So the question is, how big is this R star? Is it 1 nanometer? Is it 2? Is it 10? Is it a centimeter, right? How big does it have to be before it will not spontaneously melt again, right? So we can calculate that, okay? Here's how we go about it. To figure it out, first off, how would you do it from this? Just think calculus for a minute. Forget all your material science for a minute. From that curve, how would I figure out where R star is in calculus terms? We take the derivative. It's a maximum. At a maximum, if this is an expression, right, that expression right there, we have that. That's E as a function of R, right? That's what that red line represents. If I take the derivative, E of R with respect to R, set that equal to 0, that should be my R star value. Everybody with me? So that's what we're going to do. We have E as a function of R. E as a function of R is right here, right? It's this thing. That is E as a function of R. So if we take the derivative with that once with respect to R, set it equal to 0, we should be able to solve for the critical radii size. So let's do that. When I take this, it used to be R cubed. That becomes R squared with a 3 in front of it. This thing used to be R squared. Now the 2 drops down in front of it. When you set that thing equal to 0 and you solve for r, you get this expression. R star equals -2 times the free energy, the surface energy, divided by your volumetric change in free energy, okay? So if you knew those for your system, let's say that you're working at, I don't know, magnesium oxide, if you could look up the surface energy of magnesium oxide, and lots of these things have been tabulated, and you divided it by the change in the free energy on a volume basis, you could figure out the exact size that this thing ought to be. Yeah, question?
So is that only for spheres or all shapes?
That's going to be for a sphere. How do we know that? Because up above it, the energy as a function of r, derivative there, that was from the spherical expression. So if this was cubic or octahedral or whatever the crazy shape I put on a homework question, you would have to modify this expression for r star. Everybody see why? Because up above it was 4/3 pi r cubed, but that was the volume of the sphere. If this was just a cube, let's say it was the side length a, then when you take the derivative, instead of plotting it as a function of r, it doesn't make sense, you'd plot it as a function of side length a, it'd be 3a squared, right? Anyways. Now, do the units work out on that? Think of what the units are for surface energy divided by volumetric change in free energy. What should the units be on that? Surface energy is going to be, let's do joules per meter squared. Joules per meter squared, that's a surface energy. Divide that by a change in free energy, so that's going to be energy, joules, on a volumetric basis per meter cubed, right? If you divide that, it gives you length, right? The units are meters, length, which it ought to because this is r star, okay? Now, you can do the exact same thing. Once you've got r star, right, we figured out what it is, we can go back up to our energy as a function of our expression, this guy. We can plug in r star into that expression, and now we have an expression for g, delta g star, right? In other words, by plugging in this value of r star right here, by plugging it into this expression, we solve for this value right there, which is delta g star. Okay? We're just going to plug it back in. When we do that, you get this expression, 16 pi, the surface energy cubed divided by 3 times the quantity of your change in Gibbs free energy on a volumetric basis squared. Any questions so far? This crystal clear? Crystal clear. Okay. So the book, and I'm not going to do it here, but the book shows you that these expressions where you've got delta GV, that's the change in free energy, Gibbs free energy. If you go all the way back to chapter 16, we know that Gibbs free energy, G, is equal to H minus TS, the enthalpy minus the temperature times the entropy. So what they've done is they've plugged those values in for you, and now delta GV can be written right here. This thing becomes this right here. Okay? So they've done some math for you here. We need to define a couple terms. What is T alpha beta? T alpha beta is the temperature at which your transition ought to happen from a thermodynamic standpoint. So this is the thermodynamic temperature where you should get alpha turning into beta. Or in our case, we're doing liquid turning into alpha. Doesn't matter. It's just, when we write alpha beta, that could be any phase transformation. That's just the notation they use in this book. Okay? Everybody with me? Delta HF, that's going to be your change in enthalpy of formation, right? When you go from that phase to another phase, you're forming a new phase, so you could look up the enthalpy. We did this in chapter 16. We used changes in enthalpy already, so you've seen that. There's the change in temperature, delta T. V is the molar volume. So in other words, you could look all those things up, and you could figure out what delta GV is. Once you do that, they go ahead and they substitute this value in for your R star and delta G star equations. And you get, finally, these. Why do they do all that? Why all those substitutions? The reason why is because a phase diagram can tell you where this should happen. T alpha beta, whatever transition you care about. Let's do steel for a minute, right? Let's look up steel. Right? if we look up the steel phase diagram, remember, everything on this diagram is assuming equilibrium. So if you are at such and such, let's say you're at this line, this gray line, that's your composition. That right there is the temperature at which you should start to go from pure austenite, gamma, to a mixture of austenite and Fe3C. That is your T alpha beta, right, at that point. So that's why we like this equation, because this we can pull off of phase diagrams, which we have lots of, right? We can look up really easily things like surface energies and formation energies. And so all of a sudden, you can plug all those things in, and you can figure out what should be my activation energy to get over something. Is it millijoules? Is it hundreds of millijoules? Right? Is it smaller? So figure out what that energy barrier is from materials constants we can actually look up. Any questions so far? No? All right, let me ask you this. Next question is, and sketch this with the person next to you. Using these expressions here, look at where temperature is. Again, T alpha beta is a constant for your system. It's whatever it is from the phase diagram. But T is a variable. So you can do nucleation at different temperatures. So for example, let's say you're talking about water, freezing water. We know that thermodynamically, water wants to freeze at 0 Celsius by definition. But water doesn't actually, it's not like it touches 0 Celsius and all of it instantly freezes. It actually goes below that temperature a little bit. It's what we call supercooled. It goes below the temperature where it ought to transform, okay? So that's the temperature we're talking about. It's going below it, okay? So what I'd like you to do is sketch this energy versus radius curve for two different temperatures. Both of those are going to be below the thermodynamic transition, right? So let's say if ice is at 0 Celsius, I want you to plot it at -4 Celsius and -10 Celsius. How's that curve going to look? So do this with your neighbor. Start out by sketching R versus energy. And I want you to sketch E as a function of R for temperature equals -4 Celsius. And I also want you to sketch E as a function of R, but this time at temperature -10 Celsius. Give that a shot with your neighbor. How should it look different? Okay, let's assume that that right there is our first one. That's at -4 degrees. So that's E, well, I guess we already got labeled there, right? So you could use that and you could look up what is the R star for that and what is the delta G star for that. Okay? Now, as you move towards a lower and lower temperature, we're going to notice is that both R star and delta G star both become smaller. Okay? They both become smaller. So if we were to sketch that one, it would look something like this. Those look identical. There we go. No, they do still look identical. Sorry, rainbow pen. It's not happening. Okay? So this thing has an R star right here, a smaller R star than the other one, and this thing has a smaller delta G star than the other one. Okay? Any questions so far? So what does this mean? As you're cooling down water, you get right to 0 Kelvin, or Celsius, sorry, 0 Celsius, and you go 1 degree below, and we could draw the line. And it would be a really big R star, and it would be a really tall activation energy, because we're only 1 degree below, okay? If you go 5 degrees below, 10 degrees below, as you increasingly supercool it, what happens is the necessary size of your clump of atoms that won't redissolve again gets smaller and smaller and smaller. And the activation energy that you have to overcome gets smaller and smaller and smaller, which means that if you keep on supercooling something, eventually it's going to solidify because it's getting easier and easier. You're making the constraints required for solidification. That bar that it has to clear just goes down and down and down as you increasingly supercool it below its thermodynamically predicted transformation temperature. Any questions on that? Yeah.
So would you then, like, if you wanted to form different size those phases, like solidifying,
Okay.
keep it constant at a certain temperature?
Oh, so this is a really good question. Let me hold that thought. We're gonna get to that. Because this is just nucleation, right? So we had this magical power. Again, if these students were sort of randomly bundling around the room, I could yell pause and everybody would stop. How do you do that with atoms? They don't pause, right? So what do we do there? We'll come back to that a little bit later. How do you pause things and freeze them in motion? Okay. So again, the greater the undercooling, where undercooling is just how far below the thermodynamically predicted value, that the greater that value, then the further you are below that, then both of these things get smaller, and so it's easier to nucleate. Yeah, question?
You said like R was the size of the blob. What
Yep.
does that mean exactly?
So let me try and find a video after this class, and I'll put it in the canvas in the announcements. But when people do simulations of atoms, like I said, atoms are sort of randomly bumping and bumbling around, and they, at any sort of instant, if you could freeze time and look at it, maybe a bunch of them have arranged in a crystal structure lattice. Like maybe these students, if I gave them enough time and they're randomly not looking where they're going, they would eventually form an FCC lattice, right? A small group of them would, okay? Right, so that's what I'm talking about. When I say a blob of solid that forms, it's a solid, it's crystalline, but we don't know if that's going to redissolve again or keep on growing until we do this analysis. Yeah, question?
So is the reason that some will overcome the activation energy just because the atoms are not all at the same energy and it's just random?
They have a distribution of energies. Temperature means that there's an average energy, right? Some are going to be higher, some are going to be lower. And within your glob of solid, you have a bunch of different atoms, so some are going to be higher, some are going to be lower. The average energy of that has to clear this barrier, basically. Okay? Any questions about this? Pramit? That's a great question. Let's do this clicker question first, and then we'll do what impurities, we'll talk about what impurities do to this. So go ahead, grab your calculators. Let's try this out. The question says the following. Let me actually get it up on canvas, or on top hat. Okay, the question says the following. It says, if pure gold, so again, we're not even talking about different alloys, different compositions. It's all the same thing. It's pure gold, and it has a melting point of 1,064 Celsius, okay? But in practice, in the laboratory, it says it can be supercooled 230 degrees below its melting point. And this actually can happen. Some of these things, you can supercool them way, way below the temperature where thermodynamics says they ought to transform. In this case, 230 degrees, okay? Given that information, it says calculate the nucleation activation energy if nucleation is homogeneous, which is what we've been doing up till now. And then it says the values for the latent heat of fusion, that's your change in enthalpy, and the surface free energy are given as negative 1.16 e to the 9 joules per meter cubed and 0.132 joules per meter squared, respectively. So I'm asking for the answer in electron volts with 1 decimal place accuracy. So let's remind ourselves how this works. We've got these two expressions here. What did I ask you for? I asked you for calculate the nucleation activation energy. So you're going to be calculating this guy right here by plugging those values in. And since these energies are given in joules, you're going to convert those joules to electron volts. Let me look up the factor for you. I think it's just a fundamental charge, actually. I'm pretty sure you need to do your temperatures in Kelvin. I'm almost positive they need to be in Kelvin as well. This one doesn't matter because it's taking a difference, but that's an absolute temperature. I'm almost sure that has to be in Kelvin. Yes, good catch. Thank you. Good catch. Sorry. Okay. Somebody punch that in for me. Well, actually, that's, I guess, get your clickers answers in. Give it another minute, too. Yeah, that should work. Remember, you're going to solve for this in joules, but I've given you the conversion up here at the end of this problem to go from joules to electron volts. That will turn a very, very small number into a more normal number. Your answer should be like between 5 and 10-ish, I think. Electron volts. So both of those, T, alpha, beta, and T, if you convert those both to Kelvin, then you're both shifting them up by 273. The difference is still that. Yeah, so it's not like saying that you go from its melting point all the way down to 230. You're saying you go 230 below its melting point. Good question. Okay, another minute or two, get your answers in. That's joules. Turn that into electron volts. That's the joules answer. You're almost there. Yeah. What's up?
1064 minus 230 squared instead of just 230 squared at the end.
Wait, going Celsius to Kelvin, do we add or minus? No, you add. You add Kelvin. That takes Celsius into Kelvin. Are you saying this one, the last term, the 1 over 230? Yeah. That you can leave plain because look what it is. It's a difference in temperature. So even if you converted both of those to Kelvin, it would still be 230 because they're both on the same scale. Like we could take T alpha beta, turn that into Kelvin, T, turn it into Kelvin, but the difference between them will still be 230 degrees.
Oh, so you divide it, right?
Yep, that's it. You got it. You got it, Zoe. Okay, we're going to wrap it up. Get your answers in. Got to work faster a little bit. You're going to survive on the test on Friday. Okay, going to close the poll. The 15 of you that are left, hit enter. Okay. 6, 5, 5, 4. We're going to close it. I always feel bad. There's one person in here who's going to be heartbroken. 2 people. All right, sorry. Had to do it. 1 person. Sorry, 1 person. So yeah, 2/3 of the class are getting this right. The biggest thing that I see done wrong on this is you forget to turn it into Kelvin. You forget to turn this into Kelvin, but they'll take this 230 degrees Celsius. Remember, that's the degree of supercooling. That's how far below its melting point you got. So a lot of people take that and they'll turn that into Kelvin, but that doesn't make sense because this is a difference in temperature, right? If you melt at, or you're supposed to melt at 0 degrees, and you're now down here at -10, the difference between those points is 10 degrees. And that's the same if you're in Celsius or Kelvin, because those are on the same scale, they're just shifted. So if you wanted to, you could take T alpha beta and the temperature where you're at and turn those both into Kelvin, But the difference will still be 230 degrees between them, okay? So yeah, when I plug this in, the number of joules I get is 9.64 times 10 to the negative 19th joules. And turning that into electron volts, I get that it's 6.01 electron volts, okay? Any questions on this? Make sense? Clear? Yeah, Jaden. So if I heard you right, the question was in this first term, you've got 1064 plus 273. The reason we're doing that is because we're turning it from Celsius into Kelvin, which you have to do. But this is just a difference in temperature, and that difference of 230 degrees is the same whether you're in Celsius or Kelvin. So it doesn't matter. Okay? Okay, let's keep going. So I think it was Pramit's question, he said, how is this different if it's not homogeneous nucleation, right? So going back up to our beginning of class example, we just solved for this scenario. How does that get changed in this scenario, where now you're forming along a surface, right? What's different about that? Well, let's do the math on it. How is it different? Actually, I guess we'll do this. So let's do the same thing. We're going to calculate the critical nuclei size first in nanometers with 1 decimal place. Okay? So this is our next question. Okay, so this time we're not calculating the activation energy. By the way, 6 electron volts is pretty big still, right? It's a pretty big energy. How big does this thing have to be in nanometers is the next question. So to answer that, you've got this right here. You're going to plug everything into that. So go ahead, plug your values in there. It's going to be, if you still got it saved in your calculator, it's not going to take long. Okay, go ahead and get your answers in. We're going to close the poll. Remember, a nanometer is a meter divided by a billion. So if you're getting a tiny number, you can multiply it by a billion to get it in the nanometers. What's that? You made a mistake. The maths, they got you. A billion, yeah, 1 e to the 9. Okay, get your answers in. We're going to close the poll. Okay, I'm going to close it. Okay, here goes. Okay, and about the same fraction of people getting it right. Again, it's going to look just like it's 2 times the surface energy. The temperature needs to be in Kelvin, the same free energy from before, and this is still going to be 230 degrees. When I plug those in, I get 1.32 times 10 to the negative 9th meters. We wanted it in nanometers, there's 1 billion nanometers in a meter, so times that by 1 e to the 9th, and it just equals 1.32 nanometers. Okay? All right, so how does this all get modified for heterogeneous nucleation? Okay, we're not quite there. I forgot. We're going to talk about transformation first. All right, so we're still doing homogeneous nucleation, not heterogeneous yet. The next question is, okay, you formed a little nucleus, okay? And we know how big this nucleus has to be in order to grow versus shrink, okay? But that doesn't tell us the total transformation. So to Jaden's question earlier, he basically said, like, what if you want your final microstructure to all be that size, right? Then these things have to, you can't just have one little nucleus. You'd have to have your entire volume of liquid has to be completely filled with those nuclei, right? Or you have to have a nuclei that grows. Those are your options, right? If you want to grow a single crystal, then you want one single nucleation site that grows and consumes the entire liquid. And believe it or not, we can do that. That sounds tricky. It is tricky, but you can do it. You can actually have one single nucleation site, and then the entire solid is perfectly crystallographically oriented all the way through. And you can do this on big things. So the silicon that's in all of your devices, phones, laptops, everything, they grow great big silicon single wafers that are like 12 inches wide like this, and they grow them 10 or 12 feet tall. Down at Micron, they've got a whole bunch of these things. So you can do it. How would you do it? Let me ask you that. How would you do that? How would you grow a giant single crystal? Because right now, what's the most likely thing to happen? First off, let's ignore heterogeneous nucleation for a minute. And let's just talk about homogeneous nucleation. What's going to happen is that little particle is going to form, but another one might form over here, and then another one, and those are going to grow until they run into one another. And where they run into one another, they're likely going to be misaligned in terms of crystallographic orientation, and that is a grain boundary. So what do we do? Jaden?
Could you, like, as soon as you have only one site form, you increase the temperature to, like, rise the critical energy?
Okay.
So that way nothing else has enough energy to form, but it's still just less than the...
That's interesting. So that would keep one little particle in solution, I think I'm following you. But that thing won't grow, right? So it's a good guess. What do you think, Josh? What do you do? That's it. That's what they do. Well, that's not what they do for silicon, but that is a way that you can grow single crystals. He basically said you've got this vat of molten liquid, and you introduce something that's already crystalline, and you touch it, just one. Maybe take it on the tip of a little pin, and you touch it on the surface, and then you take that and you slowly draw it out. This no longer is homogeneous nucleation, though. That little surface that you put in there, it's like that little fleck of dust. You touch it on the surface, and then you slowly draw that thing out. So the way that they grow single crystals is not via homogeneous nucleation. You can't do it. You have to do it with heterogeneous nucleation. Now you can do that by lowering a crystal in, touching it, and then slowly pulling this thing out. And they actually do that. It's called Czochralski crystal growth. And a group last year in this class did it for a project, which blew my mind. Czochralski, Czochralski crystal growth. So again, how it works is you lower a little tiny thing inside of there like this. You lower it in, and then you slowly pull that thing out, and you consume the material in that process, and you end up with a region of crystal that is completely crystallographically oriented all the way through, which is remarkable that we can do this. So we actually do this in my lab here at the University of Utah. On Monday after the exam, I think I'll bring in some examples. You can see it. We have a Czochralski setup to do this. It's pretty cool. Okay, enjoy your Wednesday, and we'll see you here for the test on Friday.